Okay, so as I said a few minutes ago, I'm going to be doing quantitative solutions. Now, the interesting thing about the solutions subunit, it goes well into the acids and bases subunit because acids and bases are solutions also, which leads into our last lab, which is called titrations. So all this is kind of going together here. Now, moles has been our underlying kind of glue that's been sticking everything together as far as topics go. So as far as solutions go, we're talking about moles per liquid liters, not gaseous liquids, okay? So in this unit, we're talking about liquid liters. So there's gaseous liters and liquid liters. Not the same at all. Okay, so this is moles of solute. Remember last time we talked about the two parts of all solutions, solvent and solute. Solute is what's, excuse me, this is my cough, right? Lack of. Solute is what you actually dissolve into the solvent. So the definition of molarity is the quantitative aspect of solutions is moles per liter of solution. Now, it's important that that solution is both the solvent and the solute together. Because when you put solute into solvent, the liters go up. Like when you sit in a bathtub, what happens is the water goes up. So when you put solute in solvent, the solute displaces a certain amount of the solvent, usually water. So you got to include those together. Now, there's another quantitative measurement that we're not going to be covering in this class that you'll get to in 1A or 3A and possibly 2A, depending on who's teaching the class. That's called molality. Okay, there's molarity and molality. They're not the same. They sound almost identical. But for those of you who are learning English, that is a real subtle difference. It's like in Spanish, burro and burro. Not the same. They sound the same. They're not the same. One is butter, and the other is burro, an animal. Not the same at all. Okay, so we're not using molality. Molality comes into something called colligative properties, and it's moles of solute per kilogram of solvent. Sometimes they're the same. Most of the time, they're slightly different. Okay. Now, molarity is big M, uppercase M. I usually put a line under it, and I usually boldface it. But it depends on your next instructor and your textbook and whatever. Sometimes they boldface it. Sometimes they just put uppercase. I even italicize. I want to make, for me, I just want to make sure it's obviously we're talking about molarity, moles per liter. Okay, does that make sense now? Okay, so moles per liter, that means that's a conversion factor. And of course, the inverse is true as well. We have yet another conversion factor. So our unit cancellation analyses we've been doing for the past couple months is going to apply here as well. Okay, so what's the molarity of the following solution? We throw in 34 grams of sodium chloride and 3.45 liters of water. Okay, so molarity again. And we don't have moles, we have grams. So we got to convert grams to moles, put that over a liter. So we're going grams. Now you can do this in one step or two steps. I recommend 2 steps, meaning you do the top one first and then do the bottom one. If you do it in 1 step, it's 2 divisions. That confuses a lot of people. Just do it in 2 steps. So now there's 2 ways to create a solution, a wet way and a dry way. We're doing the dry way right now. So we're putting in dry 34.5 grams of sodium chloride, dry. I'm not taking a concentrated liquid and diluting it. So think in terms of when it's a dry calculation, it's a 2-stepper. For those of you who are comfortable in math, you can do it all in 1 step. Okay. All right. So let's do this. So 34 calculator time. Okay, so that's a 0.171 moles per liter, or molarity. Okay, so to do this in 1 step, you'd go 34.5, hit the divide key, 58, divide key again, 3.45. That's the same answer as far as your calculator is concerned. Okay. So we can do the opposite problem. If we start with concentration and volume, we can get mass. 2-step again. So the first thing we're going to do is I'm going to go 3 point, and I'm going to put moles per liter. Now, if we multiply volume times concentration, we get moles. Okay, so volume we're going to be using that a lot in this unit. Okay, so volume times concentration. Volume is in liters, not milliliters. Concentration is in moles per liter. So if you have milliliters, you have to convert to liters, and then that arrangement. Now we're going to be using that in lab also. And we do the very last lab on titration. In fact, titration is going to be a double lab. We're going to do 2 labs in 1 day. Okay, so we need to multiply now by liters, so it cancels. Okay, so 1.15 or 150, not 150, 1,150 grams in that solution. So that's a lot of salt. Okay, so that's kind of the same problem, just back end, front end. And again, think of it as a two-step problem whenever you're taking a drive. That's unless you've had a couple. Then it's a one-step problem. All right, any questions about that? Now you can see why in Unit 1 I stress this unit analysis stuff. I mean, we hit it over and over and over again. When you get into 1A, 3A, 2A, they're going to go through what we covered in Unit 1 in about a week and a half. And most people kind of go over their head and they drop. Dropout rate for 1A, not so much 3A, but 1A and 2A is about 60% drop because of the first 3 weeks of class, which is that's the reason why you're in this class. And so you get lots of time and practice this stuff that they're going to cover really fast. Okay. And they want to eliminate, by the way, you guys, they want to eliminate this class. Not Sierra, the state legislature wants to eliminate classes like this because they don't want students spending extra time on campus taking classes that are not going to count. Well, what about students that take 1A and don't take this class and flunk? They're going to spend an extra semester anyway retaking it, and their self-esteem is going to be in the toilet. So you end up with the same result, but students feel bad about themselves versus people that are successful the first time through. So I was at my neighbor has a PhD in chemistry, and he was a real bigwig in the American Chemical Society. So he's retired. He's always getting invited to these bigwig University of California events. Chancellors show up, and I always go, and I always tell them bottom line stuff. I go, I do this every single day, and my students need prep classes, but it wastes. And then they go, it wastes time. I said, it does not waste time. And then I give them the example of a student flunking in 1A. And they said, no, research doesn't bear out your conclusion. I said, I'm in the class every day. And I asked them when the last time they taught a class. It's been like, 25, 30 years. Have things changed in 25, 30 years? Duh. Yeah, all the time. And so they want my business card, and we need to talk to you some more. Have they ever responded back? No, but they always. Anyway, just sorry, soapbox time. One more little anecdote about this. I had a student about 3 years ago. She's the one who started the tie-dyeing lab coats. That's her hobby. She got a whole bunch of students together and we tie-dyed a whole bunch of lab coats. They were trying to close the Algebra Tutoring Center here on campus. She got about 150 students together to protest. And I gave the same speech I gave you a few minutes ago. And she says, well, Dr. Ferguson is supporting us. All this stuff is going. And yeah, they didn't close it because of her. She organized it. And so that kind of movement really worked. And that's a good example of it. Totally peaceful. It was just the administration needs to know how you guys stand on stuff. Don't be shy about standing up for yourself. And there's a lot of programs on this campus that could easily go away with the current funding that's going to go away from the feds. So keep that in mind. Okay. All right. There's I'm on record right now too, so the world is going to know, I think. Okay. Now the next type of problem I want to talk about is where we start with a concentrated solution as opposed to dry ingredients. And this is the way chemical companies and schools buy acids particularly, as they buy them as a concentrated liquid. So if we needed 4 molar hydrochloric acid, we don't buy 4 molar hydrochloric acid. Well, you can, but it's really expensive because you're just paying for water. What we do is we buy 17 molar concentrated acid. So there's less water there, and then we dilute it when we get to the lab. So you need to know how to do a dilution problem. In fact, when you apply for a job here, there's an interview, and then you have to go to the lab and demonstrate certain things that you're not going to do. One of them is this kind of problem. It's how would you make, this here? So we're starting with a 24 molar solution of sodium chloride. This is like super concentrated. This is like the Great Salt Lake in Utah, that concentrated. It's hard to sink in that lake because there's so much salt in there. You can actually go like this, and you won't sink. You're laying down, won't sink. There's that much salt in that water. It's incredibly salty. Also, the Salton Sea in Southern California isn't quite as salty, but it's a ton of salt in there. It's amazing. Okay, so eventually we want a little over 4.5 liters of 2.34 molar solution from concentrated sodium chloride. We can make that one of two ways. We do it via a dry approach, like we just talked about, or we can dilute concentrated sodium chloride to the desired amount. Okay, so if I have 5 molecules of water, 5 molecules of salt in 1 liter of water, and I put in 4 liters of water, how many molecules of salt do I have? 5. I haven't put any more salt in there, right? So we started with 5, we threw in water, we still have 5. Okay. So the initial number of molecules is equal to the final number of molecules. All right. We haven't added anything or taken anything away. All we've added is water, the solvent. Okay. If that's true, then means the initial number of moles is the same as the final number of moles. Right? Okay, so that's the essence of this problem, is we have initial moles, final mole. What differs is the number of liters of water or solvent. So the equation then is so this will tell us how many liters of the concentrated we need to put in our final container. Okay, so in this case, so this is final, initial. That's important to identify final, initial, yeah. Huh?
What does it say?
Over here. Oh, it's volume. Okay, so it's important to be able to pinpoint final versus initial. If you can't identify those, this equation then doesn't follow. So how many variables are in that equation? 4, 2 initials, 2 finals. And we know 3 of them. So we can solve for the 4th one. So we don't know the initial volume. We know the initial concentration. We know the final concentration, the final volume. So we have all right. Yeah, all we do now is just solve for the initial volume. So molarities cancel, leaves us with liters. Yeah. Yeah, I can't hear because of all the kids. And since I have old ears.
Sorry. Say directly under the problem, the initial concentration times initial volume equals final concentration. Makes sense.
Yeah, so this is the final concentration here. What was, I'm confused now. You answered a question? Okay, okay, so this is gonna tell us one of two things. It's gonna tell us how much of the concentrated we have to get from the 24.1 molar stuff. So that's going to be so we need 0.44 liters of the concentrated stuff. Now, our final volume, though, isn't 0.44, it is 4.57. So what we're going to do now is we're going to put in how much water are we going to add? Exactly. We need to add the 4.13 liters of water to bring up the final concentration to the 457. Okay, does that make sense? So the first calculation is how much of the concentrated stuff we need. And then we supplement it with water to bring up the final volume. Okay, that makes sense? So this is the key here. And we're going to use that throughout this unit. When we get into acids and bases, we're going to use that same calculation. Okay, so that's an example of a dilution problem. It's basically, this is why it works, but this is the main part. Concentration times volume equals moles. Concentration times volume equals moles. Beginning and end, they're the same. That's why we can set them equal to one another. Okay? All right, so are there any questions about this? That's what we're going to be practicing in lab today, in the dry lab. Okay, so let's. Okay, so let's talk about concentrated acids now. Okay, so you're working in a stock room, and this finicky professor wants 3.57 liters of 2.34 molar hydrochloric acid. And all you have in the back is 12.44 molar concentrated acid. You're going to make it up. So this is a dilution problem again. So we need to figure out. So we have, this is the initial, initial. And this is final. Okay, so it's going to be. Okay, so we're going to solve for the initial volume of concentrated acid, just like we did before. So the question is how to make. Okay, I want direction to follow. How would you make that solution? Okay. You'd add 0.859 liters of concentrated hydrochloric acid to 4.57 liters of water. Okay, that work? What's wrong?
It's too much solution.
Right. Because we didn't account for the liters of concentrated acid. Okay, so what we're gonna do then is subtract. Okay. Now we have a total of 4.57 liters, total solution. Now, if I say on the test how to make, I want calculations and directions. Okay. So let's do directions on a dry mixture. Let's just go back to here. Okay, so how many, we did this and we figured out there are 1.15 times 10 cubed grams of sodium chloride in the solution. How would I make this solution up? I want to make it up. Well, Okay. Right? Now, remember the definition of molarity. What's the definition of molarity? It's sort of a trick question, you guys, just as a warning. Molarity is equal to the moles solute per liters of solution. What is in the solution? Two things.
Solvent and the solute.
Exactly. Two parts. So let's go back to our directions now. What's wrong with our directions? When you get a tub of water, what happens to the water? Does it stay the same? It goes up, right, or rises. Why does it rise? Because you have a big butt, right? It goes up because your body is displacing the water. So it's got to go somewhere, so it goes up. Same with solute. When we put solute in water, the volume goes up. So if we put in 5.67 liters of water, our new volume is not going to be 567. It's going to be more than 567. So how do I modify these directions? Does that make sense? Our total volume needs to be 567. Total volume, including the solute. Solute takes up volume. So how do we do this? How would I modify those directions? They don't subtract. Grams and liters.
So you have to grams to liters instead of.
Okay. So the problem though is it's the density of dry sodium chloride versus density of sodium chloride in water aren't the same either. We have a conundrum. How can we fix it? It's a simple solution, believe it or not. It's all a bunch of reasons why it's a conundrum, but it's a simple solution. Okay, first thing we're going to do is usually we use something called a volumetric flask, and it looks like this. They're kind of cool looking. And there's a mark on there. And that mark is going to correspond to 567 liters. So we're going to put in here first, we put in here the dry ingredients. Anyway, then we add in a small amount of water, something less than 5.71 liters. We could add in anything, 2 liters, 3 liters, 4 liters, as long as it's not 571. Okay, so step number 1 is, by the way, this will be on the test. You will get asked this. So it doesn't matter, as long as it's less than, let's just say 4 liters. So now it's got 4 liters of water. What are you going to do now? Yeah, or if it's already in there, either way. Okay, somehow we're going to mix up 4 liters of water, so many grams of salt. We're going to mix it up though until it's totally dissolved. you'll notice the volume is no longer 4, it's more than 4. So now what we're gonna do is we're gonna top it off at 571. After it's totally dissolved. Then we'll have exactly 571. That make sense? Because if we don't do it that way, we're gonna end up with more than 571 liters of solution. So our molarity is not what we want it to be. It can be different. So that's one of the critical deals during a job interview for chemistry. They ask you to do this as a demo for them. Okay, so let's modify. Okay, so we'd add so many grams of sodium chloride to 4 liters of water. It could be 3, it could be 2, 1. It doesn't really matter. You need enough water, though, to have it totally dissolved. You cannot have any left over. Got to be totally dissolved. It's very important. Okay, and then you're going to totally dissolve it. You're going to swirl it around. You're going to warm it, cool it back down to the original temperature, whatever you have to do to get it dissolved. Then you're going to bring up the final volume to 571. After it's total,
So,
and you're adding more water until it's perfectly what you want it to be. Does that make sense? This question, as seemingly simple as it is, flubs up a lot of students in 1A and 3A and 2A. A simple question. In fact, a lot of SAT tests have this. A lot of entrance exams have this very question because it seems so simple. How do you make up this solution? Oh, you throw on this, you bring up the volume to total. No, you don't. You have to get it dissolved first. And it has to do with Archimedes' principle. Okay, what are you on time? 1 o'clock. I'm going to do one more interesting example. Yeah. Archimedes' principle, he asked, is when something is placed in water or liquid, the liquid will rise to the volume of whatever you're displacing. In World War II, we were making ships out of concrete. Concrete doesn't float. How can a ship float made out of concrete? In fact, does anyone ever go to Santa Cruz on the beach? There used to be a concrete ship that was shipwrecked on the beach, broken in half. I don't know if it's still there or not. How can it float? We make ships out of steel. Steel doesn't float. Yet the ships float really nicely. Huh?
buoyancy or just the fact that it's displacing?
It has to do with Archimedes. Has to do with Archimedes. If the water you're displacing, if whatever is displacing the water, if the density is less than the water, it'll float. That's why ivory soap floats. We just made soap in my organic lab over at Sac City. And they said they're all making ivory soap. Ivory soap is lye soap, very simple soap to make. And I said, why does it float? I said, well, we talked about Archimedes. And it has to do with they inject gas into the soap. That's why it floats. Otherwise, it sinks. You take Irish Spring, drop it in water, it doesn't float. Difference between Irish Spring and ivory soap is density. Who knows why ice floats. Huh?
Less dense than water.
Solid water is less dense than liquid water. That's why ice floats. There's 7 molecules on the planet that we currently know about where the solid is less dense than the liquid. Everything else sinks because the solid is more dense than the liquid. Think about our Earth. If water didn't float, if you were a fish particularly, if you drive up into the mountains, I guess we're almost there now, and you'll notice that, especially when you get up high in the granite area, you'll see a lot of granite with splits on it that are slabbing off. Why do you think that happens? This is kind of an aside, but it's interesting though. Huh? What is erosion? That's right. And what does that mean? Okay, there's another factor there too. You forgot about. Mostly, what makes that granite? Now, granite is not soft. Granite's tough. When it gets a small crack and you get water in it, and it freezes, at 4 degrees centigrade, the water expands. It becomes less dense. And when it's in there, it cracks the rock open. That's why you have to wrap your pipes in the winter. As frozen pipes burst, it's because it expands. That's why ice floats, because it expands at 4 degrees. So all the erosion caused by expanding water would drastically change the landscape. Aquatic life would be entirely different than what it is now, because lakes would freeze from the bottom up. Right now, you get a layer of ice on it, and the water underneath is 32 degrees. So the fish are fine, unless the whole lake freezes through. But if it's a deep enough lake, the ice insulates. When you go winter camping and you build a snow cave or a snow trench, inside that is nice and cozy at 32 degrees. It can be snowing outside. I used to do a ton of winter backpacking, and that's what we used to do. And I got this cozy picture of me in the snow trench, little candles along the edge and stuff. It's really kind of cool. But anyway, bottom point is Archimedes comes into play when we're mixing chemicals. And it has to do with displacement of water by something solid. Okay. I'm going to end it here. Tomorrow, I'm going to go into some very detailed versions of this. We're going to take a solution and we're going to throw in extra water into it. And we're going to figure out what the new concentration is, things like that. Okay,